All right, so this lab is going to pertain to the synthesis of cobalt complexes to look at visualizations of how ligands will affect the metal in UVVis. So we're going to use UVVis to explore property relationships between these cobalt complexes. To do that, we have to synthesize all these cobalt complexes, so we're going to be following our procedure here. First, we need to make a cobalt stock solution. I'm going to be reading this straight from the procedure. We need to prepare 25 milliliters of a 0.0042 molar cobalt-2 nitrate hexahydrate solution. How do you do that? It's giving me a molarity and it's giving me a volume. So what I have to do is take my molarity, multiply it by the volume to cancel out my liters. So that means the volume has to be in liters. Then I need my molar mass to multiply that by the number of moles by, so that I can actually get the gram amount that we need. So we came up with 0.0306 grams, which is right here. That's what it looks like. All right, so we're going to transfer this carefully to our 25 milliliter volumetric flask. We're just going to make this into a little funnel. Make sure that all of our salt goes in there. We don't have any. Now we're going to weigh our weigh paper again to make sure that we've transferred everything, or at least we can use mass by difference to get the amount that we transferred of our cobalt nitrate. Okay? Actually, it'd be cobaltous nitrate because it's cobalt-2. This beaker here. So we have 0.2282 grams. We started with our weigh paper.
Weigh paper itself is here.
4. Oh, yeah, we don't need that.
So this was with the
0.8?
Yeah, 0.8.
That's 0.8.
Oops.
All right, grams. So mass by difference here is going to give us the mass of the cobaltous nitrate that we actually transferred. Did I do that math in my head right?
Mm-hmm.
Okay, so this is what we actually transferred. Of this compound. All right. Now we need to take this, and it does not tell us a solvent. If it doesn't tell us a solvent, what do we assume? Water, because water is our universal solvent. So we're going to pull this up. Oops. Well, I didn't do that one very well, did I? Good. Now we need us a where's my stopper size on here? Number 9. We need us a number 9 stopper. It says 9. Oh, here we go. Number 9. Gonna invert and shake. We no longer see any crystals in the bottom. It's a very pale pink. We're going to still shake it to make sure it's homogeneous. That's our stock solution. All right. Now, with that stock solution, we are going to make the first complex, the glycine complex. So we need 10 milliliters of this solution. And that's 5. Nope, that's 10. That's good. All right. It is very difficult to get out of this, so we're going to have to transfer this to a clean 50 milliliter beaker. I need a waste. I'm going to use this as a waste beaker. Sorry. I'm moving too fast sometimes for Bobby. Apologize. Coat our, trying to be conservative with this that we made because we only made 25 milliliters of it. Hope I just didn't break that. All right. We have 10 milliliters. We're going to put into a clean 50 milliliter beaker. I'm going to leave this beaker in front of our stock solution so I know what it is. But if I leave it, I should label it correctly. Correct? So we say, yes, Miss Tina. Man, I miss you guys being here. You guys need to come back as soon as you can. I know, staying away for safety. All right, now we need to mix this with 0.75 grams of glycine, which we have right here. We're going to transfer this. We're basically going to do a ligand exchange. From the nitrate to the glycine, and we did not get all that for sure. But we're going to get another mass. So we know exactly how much we transferred. My balance was zeroed. 0.242. Ooh, that was freaky. .2419. 0.2419. Point 0.2419. So that difference gives us 0.7375. 0.7375 grams, and it wanted 0.75 grams. To this, we need to add 10 milliliters of 3% hydrogen peroxide. That does not have to be quantitative. You need to be careful with this hydrogen peroxide. It will react with your skin. It oxidizes your skin very readily. So there's a caution there. All right. And we got a color change, so something happened. Okay. This says to stir until bubbles stop and color stays consistent. Those are bubbles in there, not solid. So we need to wait till the bubbling stops and the color stays consistent. While this is going, we can move on to make our next complex, which is our oxalate complex. So, where's me a little stir bar? Let's just gently stir that. That I don't know what was in that. And let's move on to the next complex. So we can take another 10 milliliters of our solution that was prepared. I'm just going to use the same volumetric flask so I don't have to rinse anything or anything like that. And so we're going to put 10 milliliters of this. Oop. Didn't fill it enough. There we go. Went too low. There we go. Let's put this in another 50 milliliter beaker. Okay, so this is where we as chemists improvise, because when we looked up our stock, we do not have potassium oxalate to do the ligand exchange, but we do have sodium oxalate to do the ligand exchange. Now, if I need 1.55 grams of potassium oxalate, and that is a monohydrate, the molar mass of potassium oxalate monohydrate is 184.23 grams per mole. So I'm going to take my gram amount and I'm going to divide it by my molar mass to give me the moles that that's equivalent to. There's a 1-to-1 molar ratio of the potassium oxalate to the sodium oxalate, and my sodium oxalate has a mass of 134 grams per mole because it is not a hydrate. Okay, we do have this, and so with this math I figured out that I need 1.1274 grams of sodium oxalate. So let's weigh that out and we'll be right back. So you can pause that. Okay, we have our sodium oxalate prepared, weighed out, ready to transfer. Transferred. Now we're going to get this mass. .2319. 0.2319. Oops, sorry. So we have 0.2319 after transfer. 1.3582 minus 0.2319 gives us 1.1263, and I needed 0.1274, and I've got 0.1263. That's going to be close. So we're going to go with that. To this, I'm going to have to add 10 milliliters. Is this one I use for my peroxide?
Yes.
This is the only one I have out, so it had to be. That's going to be close enough to 10. We need to heat this gently to 30 to 40 degrees for 10 to 15 minutes. So I have a second beaker of water on here so that I can monitor the temperature without putting my temperature probe actually directly in my solution. So this water is at 27 degrees. While we're waiting on this one to get up to temperature to start timing, let's check on our first complex, the glycine complex. And here we have our glycine complex with no more bubbles. And I think our color has stabilized. So isn't that a pretty purple color? I know, I hate you guys aren't here in person because these colors are going to be really cool with these inorganic complexes. So this is complex 1. This is cobalt with the glycine. Okay. Our oxalate complex is being made. Okay. We're almost at 30 in that one. Pretty pink color right now. All right, so let's move on. Now we need, okay, steps 5 and 6 for this have to be done quickly. So we're going to have to move quickly. So if I don't talk a lot, forgive me, but this has to be done pretty quickly. Okay. So it's suggesting that I gather all the necessary materials before I even start on this. So let's do this. We need 0.6 grams of cobalt 2 nitrate hexahydrate, 10 milliliters of water, and 2 to 3 drops of 30% hydrogen peroxide. So let's combine that in another 50 milliliter beaker. 0.6 grams. .6, so 0.82, 8, said 0.6 grams. Okay. This is what you used?
Mm-hmm.
I see a little speck on there. We're going to just clean it off, make sure it's clean. So we need 0.8282. 8282. Metal complexes are often toxic, so you do not want to expose yourself to these if you don't need to. Well, I can't even get a crystal off. Alright, 0.8280. It keeps toggling between 80 and 79. Point 8279. Left my beaker over there, didn't I? Let's just do this then. I'm going to transfer this. Point 8279. Point 2286. 0.2286. Grams. So that is going to be 9. So which is 8279 minus 22.2286 950. That's pretty close to 0.6 grams cobalt nitrate, and we're doing this for step 5, number 5. All right, do I have my grams for everything else that I need on here? This is sodium oxalate. This is the glycine. This is my glycine. Alright. Got to keep all this together, as you well know. And I will put it in a notebook. Check our temperature. We are at 31, which means this is at 31. So we are going to time this for 10 minutes. Oh yeah, it's still cool enough for me to touch, so we're good. All right, now, in this, I need to put, this has got to go fast. So, we need 10 milliliters of water. I don't know what this was for. We're going to get a fresh one. Expended glassware over there. Alright, so we need 10 milliliters of water. that, we're going to have to add 2 to 3 drops of 30% hydrogen peroxide. So we're going to get our hydrogen peroxide. %. Really bad stuff. 3% is bad. 30% is really bad. There's our dropper for that. And we need 4.52 grams of sodium bicarb with 10 mils of water, 2 to 3 drops of 30% hydrogen peroxide. And so we need to dump this together and stir until just boiling.
Should we prep the solutions off camera?
Yes. We're going to go ahead and get all this stuff together before we actually put it together. So we can. Okay. Here we have our 4.52 grams of sodium bicarb already added to our beaker. That's going to be looking ahead, reading ahead. I noticed that the beaker needed to be large enough for the gas evolution of what we're going to mix with it. So we're going with this volume. Hopefully that's going to be enough since this is the first time we're doing it. To this, we're going to mix 10 milliliters of water. All of the solid's not going to go in, but that's okay. It told us it wouldn't. We're going to start mixing that with the stir bar. We're going to put in 2 to 3 drops of 30%. That's 3 drops. And we have to heat that to boiling. All right. So while we're heating that to boiling, let's go ahead and add our water and our 30% sodium hydroxide to our original cobalt nitrate, cobaltous nitrate. And
Hydrogen peroxide.
It needs 10 mils of water. And 2 to 3 drops of 30%, which is already in here. Okay. Now what I'm going to do is, once we're boiling from that solution, for the amount of time that we need to boil it, then I'm just going to remove that from that hot plate and put it on this hot plate since this is fairly cool. Turn off the heat and let it stir after this one's complete, which is going to take about that time. This solution is at 32 degrees. And we only have 1 minute left. We have 1 minute 13 seconds, so we're almost done with our first complex. The second complex. This is the Oxalate Complex. Alright, we're going to transfer this solution over to our other hot plate. And we're going to mix these two. Wow, that changed colors.
Which complex is this?
Stir until the bubbling stops. Quickly move to step 6. All right, we have our sodium bicarb with the water and 3 drops of 30% hydrogen peroxide that we are now, since this is boiling, we're quickly going to move it to a different stir plate. We're going to stir it while we add our cobaltous nitrate. And then when that stops bubbling, we're going to quickly transfer 10 milliliters of that into another beaker, swap off that so that that can stir, and we're going to add our 40 milliliters of nitric acid until no more bubbling and no further color change. All right, so if this turns dark brown or black, it's bad. This is the color of our first one. We're gonna see if we can match that one. All right, so let's go. We're still stirring. We're gonna add this. Woo! There's no more bubbling, so we're gonna take 10 mils. Ooh, is it still bubbling? Oh, it is. I don't see any bubbles now, but it's really dark. It's hard to tell. We're going to take 10 milliliters of that. Put it in a different beaker. And to this, with stirring, we're going to add our 40 milliliters of nitric acid. And we got the same color. Well, almost. That's more teal. That's more teal. This is more blue-green.
Say it's darker.
Blue-green, it is darker, isn't it? Well, we will use the one that did not stir so long because I think this one's going to be more accurate. Okay, so we're going to take this and replace this with it. That's our color differences. And so we may have let this one stir too long before we added our nitric acid to kind of quench it. So this is what we're going to, this is the one that we made where we did it quickly like the procedure said. We're going to follow the procedure. Okay, so now we have our glycine complex, we have our oxalate complex, and we have our water complex. Now we need to make our phenanthroline complex. Okay, so for our phenanthroline complex, we're going to save a portion of this solution and then use the remaining for step 7, which is our phenanthroline complex. So, let's save a portion of this. Ooh, that does not look clean. You guys did not clean your glassware. You're not here for me to fuss in person. So we're saving some of complex 5, and we're going to use this to make phenanthroline complex. All right, so we need 10 milliliters of this. We have used so much. We're running out of glassware here. Three rinses. Analytical chemistry, 3. Magic number. 3 rinses. Okay. We need just a tad more. There we go. All right, 10 milliliters. Combine it with 0.115 grams of 110 phenanthroline. Ew. This is going going to take more than what I thought. You look at these spikes. You got to see these spikes. There's spikes in there. It's pretty. Ooh, pretty spikes. .115. .115. All right. So to 10 mils of this, I'm going to add this. And I'm going to add 10 mils of 3% hydrogen peroxide. And we need to stir that for 10 minutes. So I need to get another stir bar. Man, you use so much glassware in here. Aren't you guys glad you don't have to clean all this glassware that's being used? Ooh, that was a different color. Let's stir this. Kind of peachy. Better get that off the stir plate. So that has to stir for 10 minutes. Then we are not going to be making the cyanide complex, but we will use our cobaltous chloride complex. So we're just going to make a 2.55 oh no, we don't need that much. The reason we're not making the cyanide complex is if you guys were here, potassium cyanide is way dangerous, and I would rather you guys not handle that, because it even says on the bottle that contact with skin will cause or may cause death. And so yeah, it's something we really don't want to mess with. So we're just going to make a cobaltous chloride hexahydrate complex, but we don't need the amount they have here. We probably need about 20 milliliters of this, so we're going to scale this down. So what we need to do is, if we have 75 milliliters for our volume, we're just going to set up a ratio. We need about 20 milliliters of volume, and so we need grams of cobalt chloride here, and this solution takes 2.55 grams of cobaltous chloride hexahydrate. So we're going to find our X here. .55 times 20 divided by 75. So we need 0.68. Is that logical? We have less than half of this, so we have less than half of this. Logical. If you want to check your math again, do so. So we need 0.68 grams of cobaltous chloride, and we're going to put that in 20 mils of water. Always make sure your numbers are logical when you're working in lab. What would be an illogical number? If we would have come up with something way low or higher than what we started with. That would have been illogical. We need 0.68. These crystals are pretty too. Pretty magenta. See how pretty they are? I knew I was going to go over with that one. So we're just going to mix this in 20 mils of water. Since it is a chloride salt, it should be soluble because it's not one of our compounds with chloride that's not soluble, which is what? Silver, mercury, lead. There's another one in there.
Phosphate?
No, not with chloride. Silver chloride, mercury chloride, silver, mercury.
Barium? No.
Nope, that's soluble. Ah, there's another one. Can't remember it. There's another one. All right. That's a pretty color too.
What complex is stirring here?
That is our phenanthrylene, orthophenanthrylene with cobalt. And it has 4 minutes left. And this is our cobaltous chloride. So, cobaltous chloride I want to play with this. I want you to see what Le Chatelier's principle does when you take a little bit of this because remember that has some water in it. So let's take a little bit of this, and you see that color. And you actually did this in general chemistry. You may remember it, you may not. We're going to take just a few drops of concentrated hydrochloric acid and watch what happens to the color. Woo! Isn't that pretty? That's where they get cobalt blue from, because cobalt makes that pretty blue color. So this is actually cobaltous chloride with only chloride ligands on it, and you've still got some water around that chloride that's pink. So that's. Should we take a UV of this?
Yeah, sure.
Yeah, let's do this. We're altering our procedure as we go. Yay! we have
Hold
our,
on. Start over.
okay. So here we have our cobalt complex with glycine as a ligand. Here we have oxalate as a ligand. Here we have our water complex. Here we have our phenanthroline. Here we have our cobalt with 6 waters on it. And here we have our cobalt with 4 chlorines on it. Or chloride, sorry, chloride ions.
And this is still cobalt chloride with the hexahydrate. You said cobalt
Yes,
water.
but when we added the water to this, Le Chatelier's principle kicked in and it moved it to the water complex. Okay, so it's in equilibrium. So this is what it would look like if you have cobalt chloride. Well, actually, that would just be cobalt chloride, and then you have water added to that. It's going to set up an equilibrium. This should actually be 4, 2 minus. I'm making a mess of this. But anyway, this is going to be 2 plus 4 Cl minus. Okay. So once we added this bulk, we increase that concentration. Le Chatelier's principle shifts to the water complex side. That's how that works, because we had an overabundance of water compared to our cobaltous chloride complex. All right, so let's go. Now we'll meet back at the UV. So we've done our blank with water. We've selected a scan range from 325 to 750 nanometers. And we are hopeful that that is going to get all of our lambda maxes in. So this is our first purple complex, which was, what do we make first?
Glycine.
Glycine. Glycine complex is purple. Which we would expect it to be on the 400 side, right? Because Roy G. Biv, violet, is on that lower end. Started going up again, so it's got more than one peak, but for us, it looks like this is the lambda max. It's not changing absorbance in there, so we're going to average that to 385. Let's write this. Oh, let's save this. I have my flash drive in here, so we're going to save it. We're going to export to USB. Okay. Just in case something happens with the data, we've got our cobalt glycine at a lambda max of 385 nanometers, and it is an absorbance of 0.366, although I don't know the absorbance is going to matter for us as long as it's okay. Waste beaker. We need to rinse this between, because we're not doing a standard curve with the same compound. We're doing different compounds, so we need to rinse in between. And we need to rinse our cuvette with this in between, with your next compound that you're going to take a UV of. That's such a pretty pink.
This is the oxalate.
This is the oxalate. Cobalt oxalate, which is C2O2. have a lambda max of, ooh, I don't know why it did that. It's weird looking. This is a little pink, so we would expect it to be a little in that direction. Ooh. Uh-oh. This is going to go off scale.
Let's say have that one is the lambda max. The
Do what?
537.
Have that one? Staying at 0.54. So let's go with 534. And we'll write down the absorbance just in case. I don't think it matters. We just want our lambda max because you'll need to explain why the cobalt, because remember this is all cobalt. And what gives the colors in our complexes is typically the metal and the different electronic states that the metal is in. And so you're going to need to explain or talk about why there's such a difference in colors with the cobalt. Well, let me put that back in there. I'm not reusing that solution. This one is the water complex. Yeah, it's a blue-green, so I would expect it on the 400 side to be a little higher. I didn't save that other one, did I? So $3.99. I need to go back and run this one at the end. I did not do that one. I didn't save it. yellow, which is the cobalt, phenanthrene. Phenanthrene, sorry. Phenanthrene. That's yellow. Why isn't yellow closer to the middle? That's over 2. Can we use that if it's over 2?
This is in the UV range anyways.
Huh?
No.
No. 451? I almost did it again. That one's more pink, so it should be. Why is it in the green region? For Lambda Max. It's over 1. 512. I don't know if that's going to be accurate. Should we dilute it?
Should be fine.
Since we're just doing a lambda max and we're not getting an absorption for a standard curve of quantification.
Right. Save it.
Oh, thank you. This is our one that we added just for fun. I don't know what this one's going to do, but we're going to see. Uh-oh. It's way too concentrated. Well, that's weird. So it's going to be in there? Why do the colors not match up with my spectrum here? If I just take the middle of this, this is the one we added. It's above 3, so. But this one's tricky, because if we start adding water, we'll exchange the ligand. So this one we added was a bust. We're not gonna do it. All right, I will clean up stuff and then I will post what you need to Canvas and you can view and write up your report. See you later.